dimensional urban data, allowing objective identification of homogeneous zones, anomalous patterns, and spatial functional groupings without requiring label data. Thank you. Welcome back. In module 9, we will be doing unsupervised learning, and lecture 41 we will start clustering, and this is part 1 of in a series of 3 lectures. So the different concepts that we will cover in this lecture will be, we will remind you about what is unsupervised learning, then we will talk about clustering in general, and finally we will move into the different clustering models, and within those models we will start discussing about k-means algorithm in this lecture. And then we will solve a problem of grouping different urban zones into different clusters using the k-means algorithm. So coming to unsupervised learning, it is of course it's unsupervised. So that means learning works with data that has no labeled outputs. That is, we don't have any predefined target variables, and that means it is a different. Earlier we have learned that for every x there. For a group of variables, we have also a target variable, but in this case there is no target variable to guide the particular model development. So this particular algorithms will focus on discovering hidden structures or patterns within the input data, and the different types of algorithms that we will deal with are the clustering models, then there are the association models, and then of course the dimensional reduction model. Now, clustering models, as you understand, the pattern is to try to find the clusters in the data. Association models are trying to find the association, that is, if x is present, then y is also present, something in that manner. And underlying groupings or dimensional reduction actually talks about that in a high dimensional feature space, not every feature has got the same impact, only a few features have got more impact, and to identify those right features and the groups of features which could be clubbed together, there also we can, in that way we can reduce the dimensionality. So that is what the different types of algorithms we will cover under unsupervised learning. And of course the first one is clustering, and that would be the focus of this particular lecture. And unsupervised learning is primarily exploratory and descriptive in nature. So what it means, like, before we actually do predictions, we may need to categorize data into different groups so that we develop different models for them or different prediction methodologies for them, because the same prediction model may not work accurately in both the data groups because of the nature of the data. For example, I am trying to predict education level, right, of different groups. So that means in different it may, or rather I try to find the buying behavior of different population groups, right. So obviously the buying behavior would not be same for different people belonging to different income categories. So that means there may be a need to segment the population further. So what are the features based on which we can further segment the population, or what would be the clusters we need to first identify. So these are the kind of tasks that is first undertaken before we do the actual prediction task. So this is this unsupervised learning is something which actually help us to do that. So it helps us to do pattern discovery, it helps us to do segmentation, it helps us to do dimensional reduction, and so on. So coming to clustering, what it does is it groups the unlabeled data set into different clusters of similar data points, and the objects in a group has less or no similarities with another group. So that's the objective, that means to group data points which are more similar in nature. And this is achieved by determining the presence or absence of similar patterns in the unlabeled data set, like shape, size, behavior, whatever the features are. And this algorithm, of course, because it's unsupervised, it doesn't require any supervision. And we see this kind of algorithms used in many things, such as the recommendation systems for Amazon, Netflix, or any kind of app where when you watch a movie, you get recommendations for another movie, or when you buy a product, you get recommendations for another product, right? Then market segmentation, then social network analysis, image segmentation, statistical data analysis, anomaly detection. So in many fields, we actually find the use of unsupervised learning, and within that, clustering. So, if you see this particular image, what you will see over here is that we have got several fruits all mixed together. One is banana, one is watermelon, and then there are berries. Now, the unsupervised learning algorithm, what it does, it helps us to group these particular fruits into 3 separate clusters, so that each of these clusters match itself, it is more near to each compared to other clusters. That means you see berries together and then bananas together and then the watermelons together. So, the purpose of this algorithm is to find the right, is to predict the right grouping of the different data points. So, this clustering could be of 2 kinds, hard clustering and soft clustering. Hard clustering is when data points belong to only one group. Soft clustering is when data points belong to more than one group. So, these are the 2 kinds of clustering. And different clustering methods suit different spatial and density patterns, making them useful for analyzing heterogeneous urban and geographical data sets. Now, what it means is when we have a mix of data, the characteristics of the mix could be different, right? Sometimes though certain areas have got higher density, certain areas have got lesser density, some of the features are similar, some of the features are dissimilar. So, depending on the nature of the data or its application, we have to determine which way to cluster it would be better, right? So, and the second thing is clustering is primarily designed for numeric data. Why? Because most of the algorithms that we will use in this particular, in clustering are like distance based. That means it somehow or other measures the distance between the points, right? Because it is talking about clustering. And so that means we have to depend on numeric columns. Now, categorical data definitely can be used. In that case, we have to first encode it. That means we have to use one autoencoder or any other way to encode the data into numeric values. So, it could be even converted into zeros and ones and so on. Then obviously, if categorical can be done, ordinal data also can be done. So, that means it could be treated as we can always take categorical data and we can also put in some form of a numeric scaling, or we can do proper scaling to convert it into numeric form. That can also be done. And then there are some special algorithms like K prototypes which could be used for mixed data sets, which includes both numeric and categorical data, right? So, we can have these options and as per the nature of the data, we can use different ways to categorize them. So, similar observations or data points with comparable characteristics are placed in the same cluster to reveal natural groupings. Now, the purpose of this is to identify similar trends, geographic trends, hotspots, like where is something is occurring more frequently than other places, and then certain kinds of, and sometimes this kind of analysis reveals that certain underlying structures in the data set, like I can find that, okay, which are the routes where more trips are happening, or which are the OD pairs which are more frequent, or in suppose we are using IoT data, we can see that, okay, similar patterns being observed across the data set, or sometimes there are anomalies that also could be detected, right? So, that means if we are able to determine patterns, we can also determine anomalies that doesn't match the pattern, and that actually shows that there is some problem there. So, that means anomaly detection could be also done via these methods. Now, coming to different clustering models, so we will start with partition clustering first, and it's a distance based clustering method where we use centroid as the base distance base which we use for clustering, and we can divide the data into different non-hierarchical groups. So, that means there is another way to divide the data which could be based on distance, which is hierarchical clustering. And there hierarchical clustering means within clusters there are other clusters, right? But in this case there is no such concept, it is for non-hierarchical groups. That means different distinct clusters would be found out. So, over here you can see the different data points all spread across. Now, we have zoned them into first, second, third and fourth zones, and each zone have got different types of data. Maybe in this case it is based on the shape. I am also trying to determine the the centroid of this data set. Of all the different points that are there, we are finding the centroid, and what it says is that means using the centroid, we are trying to define how the clustering would happen. Now, one of the most popular algorithms in this approach is the K-means algorithm, where we use centroid as the measure for distance. and the data set in this case is divided into predefined clusters. That means we decide that okay, let us divide the group into 3 clusters or 4 clusters, something like that. And then what happens is so the logic that we follow is the distance between the data points of within one cluster, right, from its cluster centroid is minimum compared to other cluster centroids. That means whatever data points are there in this particular cluster should be more near to this centroid compared to centroid of other clusters, right. So that means that this data point belongs to this group because it is more near to its own centroid, right. So that also means that the division that I have drawn is appropriate. So when this happens, then we can say that well, all these data points are now clustered towards its own centroid, or it is more near to its own centroid compared to other centroids, so it's an appropriate clustering. So so algorithm finds centroids mu k that minimizes within clustered square Euclidean distance. So that means within cluster squared Euclidean distance means the distance between each points to its centroid, and we measure the Euclidean distance, right. So when that is the minimum value, then only this can happen. Data set is classified by dividing the samples into different clusters of equal variance, right. So that means all clusters are expected because it's the same variance, right, and expected to have spherical and shape and equal spread or size of that variance, with data points within each cluster being close to the centroid. So that means because all the clusters have got similar variance, so automatically it will try to assume a circular shape, right. But it may so happen that we are not finding that circular shape, right. So that means it has got different variances. In that case, probably this would be not the right model to use. So that means some of these clusters could be elongated or can have different densities. That means k-means better algorithm is not probably k-means for this case. In that case, probably we should go for clustering algorithms like Gaussian mixture models or DB-scan, which are mostly more appropriate, right. So that means k-means clustering usually is for data sets where densities, we don't find that much dense, in certain portions are denser or something in that way. So we have to also, based on the nature of the data, we have to decide which algorithm would be suitable. So this algorithm could be used to segment people, zones into k groups, such as, like for example, we always have satisfaction data when we do a survey, like how much is highly satisfied, which group of people are highly satisfied, neutral or dissatisfied, or different, if we want to find out distinct travel behavior profile. So then we can want to use this k-means clustering to find out which data points of it can have many features in the data point and belongs to which cluster, right, show similar tendencies, right. So Likert scale perception segmentation after scaling, then travel mode clustering, zone classification with continuous indicators, all these things could be part of the k-means process. So let us look into the algorithm that we use. So in this we will follow the images over here in sequence from here to first this is 1, this is 2, this is 3, and this is 4, then 5 and so on, right, 6 and 7. So step number 1 is to choose the number of clusters. So in k-means algorithm we have to start with a specific number of clusters. So in this case, let us choose 2 clusters. So you see this is 1 point and this is 1 point, right. So choose random points or centroids for each k different from the data points. So we add these 2 centroids randomly, right. Now because we assume them to be centroids, actually they are not, but we assume them to be centroids, what we do is we also the next step is we draw perpendicular, we join these 2 centroid values and then we do a perpendicular bisector of that, right. So when we do that, automatically what happens, we can assign data points to the closest centroid, and that can only be done by a median line is drawn between both the centroids. So we can do that by taking a perpendicular bisector, right. So this is the median line between the 2 centroids, and anything which falls on this side belongs to this centroid, and anything which falls on this side belongs to this centroid, right? So we can say that these points are more near to this centroid and these points are definitely near to this centroid. So obviously, because it falls on that side of the median line. Now the step 4 is to calculate the variance and place a new centroid for each cluster by calculating the mean or the average position of all data points assigned to a particular cluster. So we measure the variance also. That means, that's a score measure to show how good is the clustering, and then we also calculate the mean and we move the cluster centroid from here to here, and similarly this one moves to over here. So these are the new centroids, right? As soon as we get the new centroid, again we connect them and we draw the perpendicular bisector, and I get a new set of data points, and I keep on shifting the this mean again and again. This mean, shifting of mean is a very common thing in clustering, right? So once we have done that, eventually at one point of time you will see that there is not much difference, right? So once or there is no change in that particular movement of that particular centroid, and then we can say that clustering is achieved. And now you can see that we have now able to segment these two data this data set into two different clusters. Now how do I determine when to stop, right? Or how many clusters is good, right? So we use a measure called WCSS, or within cluster sum of squares. It is a method to find the optimal number of clusters, or rather the method is elbow method to find the optimum number of clusters, and the statistics that we use to do that is WCSS, right? So what it does is it measures the total variation within the cluster. Now total variation is basically this norm of x minus mu k whole square. Now that means that for all the different vectors we are adding up the differences and then we are taking a square of it, right? So that's the norm. That's why we take that this thing. So WCSS is a metric used to evaluate how well the clustering has been performed by measuring the compactness or tightness of the cluster. That's the purpose why we do that. That means the more tight is the cluster, less would be the variance. Then WCSS represents the sum of squared distance between each data point and the centroid of its its respective cluster. So that means it's the sum of the squared differences between all data points and its cluster, right? And the lower the WCSS value indicate better clustering, because points within each cluster are closer to the centroid, and meaning that the cluster is more compact. So that is the measure, and we take a summation for all the different clusters as well, and then this actually checks the cluster tightness. And what we have done over here, you can see that for the same data set, I can use 2 clusters, 3 cluster, 4 cluster, 5 cluster, and as we do that, we can, for each clustering, I can calculate the WCSS scores for each, once the clustering is done, and then we can find that the curve looks like this, and at this point, you can see there is a definite bend in the curve. That means from point this to this, the change is drastic, but from here to here, from this point to this point, the change is not that drastic, right? So that means there is not too much compactness achieved by further clustering the data. So actually it may lead to more unnecessary cluster, creating cluster. So that actually this process helps us to identify which is the best possible way to do that. So this elbow plot, or the way we can just see that where the WCSS scores are not changing much, and then we can adopt that. Now, along with this measure of compactness, which is WCSS, we can also see something more. That is that means along with compactness, we can also see the separation between the clusters. That is the distance between the different clusters, right? So if both of them are high, then probably it's a better measure, or both of them could be measured, and together they gives a better measure, which is known as Silhouette score. And it evaluates both compactness and separation between the cluster, and it could be used for validation. That means once the data is clustered and all, we can use it to validate if the value is improving or is better or so. So in addition to k-means clustering, we can have k-means plus plus. This is we in the different machine learning algorithms and the different libraries, we find this particular mention of k-means plus plus strategy. So what it does is initializes the initial centroid, which was random earlier, leading to bet. So it is a way to do that instead of doing it randomly. So what it does, that means the centroids are spread out, reducing the chance of poor initialization and improving convergence speed. So instead of randomly doing that may lead to very nearby centroids, I can make sure that those from the initial time period itself, the centroids are spread out so that the convergence will happen faster. That means the number of iterations will reduce. So this is, you will find that in many cases this is default, but in some algorithms we have to also give it. Now, how to measure the Siloid score? It measures how well each data point fits within its own cluster compared to other clusters using both intra-cluster distance A and nearest cluster distance B. That means within the cluster what's the distance, and from the nearest other clusters, this point also measure what is the distance. So this ranges from -1 to +1, and where higher values indicate better separation and well-defined clusters. And you can see the measure is given over here, SI equal to BI minus AI, and then divided by max of AI or BI. Now what is AI? AI is the average distance from point I to all other points in the same cluster. So this is intra-cluster distance, right? So this is compactness, and separation is minimum average distance from point to points from point to points in the nearest neighboring cluster. So this is inter-cluster distance. So from that cluster to the other clusters, what is the nearby clusters? What are the distance to those points? So the Siloid value is given as like this, and if we find that AI is lesser than equal to BI, then point is well clustered in most cases, and SI value will be something like around approximately 1. Then AI is almost equal to BI, then SI value equal to 0, and then point lies near the boundary. And if AI is greater than BI, then possibly this is misclassified. That means SI is lesser than 0. So that we have to be careful about. So we will always want it to be above 0, right? So the overall Siloid score actually has to be calculated for model validation, and this final score is the average of all point-wise Siloid values. That means we take a summation, we measure for one point, and then we take a summation for all points. That is I equal to 1 to n divided by 1 by the center and summation of SI and divided by 1 by n, right? So that means we take Siloid score, calculate Siloid score for every point, and then we divide it by n. So to explain this, we will use this particular example or CSV file, which is the urban zone or street segment file. What we have done is for each street segment and the surrounding zone to it, we have determined that what is the population density of that area, traffic volume of that area, land use mix of that area, average speed, parking demand, footfall, road width, this public transit access, all this data we have got, right? This data units, you can see public transit as access is using an accessibility score from 0 to 10, how much far away it is. Road width is in meters, footfall is in pedestrians per hour, parking demand is in vehicles per hour, average speed is in kilometer per hour. Then land use mix is basically an entropy index, where we have used 0 is single land use and 1 is highly mixed. Many kinds of land use are mixed. So the value ranges from 0 to 1, right? Then traffic volume is vehicles per hour and population density is persons per hectare. So this is given in this particular CSV file, and the data set, as you can see, there is no target level. We are not predicting anything. The goal is to discover the natural groupings of the urban zone based on traffic, land use and other mobility characteristics, which zones are similar in nature, right? So the program, the first part, as you know, is pretty standard. We have already done many programs earlier. Import pandas, import numpy, import matplotlib, then we are doing using this imputer. This is simple imputer. You know what's the use of imputer to replace the missing values. Then we are doing standard scalar to convert from categorical to numerical data, and then we are importing k-means from sklearn and also importing Siloid score from sklearn. And then we are also bringing in something called principal component analysis. We have a dedicated lecture on this later on, but what I would like to say over here is PCA is a measure in which we can reduce high dimensional data into lower dimensional data, right? So that we will talk about and why we require it here. So, data file is this d:/urbanzones.csv. So, we are reading that and storing it first, and then what we are doing is we are also selecting the numerical columns only, right. So, we are not choosing the other columns. If there are no, we are also given a check if the numerical columns there are nothing, then we can print out that no numerical columns have been found. But here there we have got plenty of numerical columns, and once we do that, we are copying that numerical columns in X. So, that means X should be used, and then we can print the shape of the data like over here, that is 12 and 8, that means 8 columns 12 rows, and then we can also print the numeric columns used. So, whichever columns have been selected, their names are being printed over here like population, density, traffic, volume, parking, all the ones. And then we do imputer, we use imputer.fit_transform to to check if there are empty values, and then we put those empty values as well. So, that is and the new data set is x_imputed. Then scalar, standard scalar we are using to scale that values, like we are scalar.fit.transform of x imputed, and then once it is scaled, we are storing it in x_scaled. This is the standardization process, right. These are pre-processing steps. And then we start with this trying to determine which k value is better, right. That means what should be the appropriate number of clusters in this particular case. So, we are creating this list of called inertia, and then for k in the range of 2 to 7. Now, the question is, in this, because we know the data set, we know that it cannot be, the number of clusters cannot be definitely less than 2, and it can go till 7, right. We have given a value of 7, but sometimes we don't know, right. So, you have to be giving a range like that. So, for each of these ranges, we run the k-means program, the k-means function or algorithm to determine that you can see the function structure is k-means n clusters. We can give number of clusters we want. The random state is 42, that we know what it is, n in it equal to 10, which means that we will run the algorithm 10 times and also calculate the WCSS scores, and each time the starting initial centroid would be different, right, and we will choose the model which has got the best WCSS score. So, once we have done that, then we run it, we fit the data, and then we store the value of WCSS in this inertia list, right. And once we have done that, we can print this particular list, and you can see that is being printed over here. So, this is the list that gets printed for k equal to 2 to 6, right. And once we have done that, then we can plot the figure. So, once the using this plot.show, and you can see this is the curve that we are getting, and we are putting number of clusters and inertia. So, we are in the different x and the y levels, those things that we are doing. We are putting a title which is elbow method plot, and we are also showing. Now, k equal to 3, then we are assuming, right, but you may also, based on WCSS score, you can select it using just by a criteria that where the WCSS is changing to a higher degree, and you can create that criteria to select the right value of k. But here, just for the sake of simplicity, we have looked into the graph and chosen k equal to 3. Suppose, actually you cannot look into unless you run the program, but we have ran it, and then we for explanation we have put k equal to 3. Now, once we have done that, then what we can do is that we are calculating the silhouette scores, and after I run the model with k equal to 3, and I can also now predict that what would be the values, right, and then we stored that the name of the clusters and all this, and then we can print that as form of that number of clusters and the number of data points in each of these clusters, right. And for each of these clusters, we are calculating the silhouette score over here, which is we are giving the input as x scaled, that is the data set, and clusters which is over here, right. So, that means this is the model. So, using that we can create the data silhouette, we can calculate the silhouette score, and we are storing it in SIL, and we are printing the silhouette score as well. So, over here, this is the part, of course, I am explaining in detail over here. So, you can see the print n clusters actually prints the cluster count, and then for each of this cluster count, we can also see the data. That means we can, first of all, it has sorted it using the sort underscore index, and it gives the count, the lowest first and then the highest ones. And after that, we can preview the data using data.head, and that will actually print out the number of rows and to which cluster this particular data point belongs to. So data point 1 belongs to cluster 2, data point 2 belongs to cluster 0, and so on. Now the silhouette score is finally printed, which gives for k equal to 3, this is the silhouette score, and because it is more than 0.1, we can say that the clusters are well separated and compact, and suggesting that k equal to 3 is an appropriate clustering choice for this urban data set. Now over here, just for the because we have printed here only the top 5, we can actually print for all the 12, and you can see this is how the clustering has happened. And you can see cluster 0 is basically pointing towards very high density traffic, footfall, commercial cores. Then cluster 1 is low density, high speed, low activity, peripheral residential areas, most likely of course. And then cluster 2 is intermediate mixed use corridors. So you see, this is the inference which help us in urban planning. That means I can categorize these zones into different clusters based on the cluster. I can try to put their characteristics, like what is the average traffic speed in those zones, what is the traffic volume, and from there I can see the significant difference in those values between each of these clusters, and then we can comment like this, that what is the nature of that particular cluster. So this actually is before I develop any model on its or something to predict like what could be the number of accidents in each zone or something, we can categorize and then we can develop models for this that will give us better result. In the second part of the program, what we have done is we have tried to also plot this, right? Now you could have avoided it, right? We could have avoided it, but here I just, for the sake of how to plot this particular data, we are showing you this particular thing. Now what has happened is, because this is a high dimensional data set, that is, we have multiple features, right? It is not only traffic, it is not only something else. So there are, for example, 8 or 9 features, right? So when I'm doing a scatter plot, I cannot plot 8 features, right? I cannot plot all of them together. Then I require a different way to do that. So over here, what we have done is we have reduced the number of features and turned them into some latent constructs. That means which represent a group of features and which are actually linearly combination of multiple other features. Some features are neglected because they have no impact and on that overall data structure, and only the features which have got impact, but they can also be clustered together to show similar impacts, right? So that means those features are more correlated, those are combined together, and in this way when I combine, we can use principal component analysis. So we will definitely have detailed discussion later in its we have a separate lecture for this particular analysis. We do this analysis again and again, but over here we have to do it because that data set has to be reduced to only 2 features, right? Otherwise we cannot have this xn this xy scatter plot, right? So this is what is happening over here. First we are scaling the data using we can converting the data, reducing the dimensions of the data using PCA. So we are principal component analysis, we are stating that we require only 2 components. We don't want many components, we require 2 features. And random state 42 remains same. Then once we fit the model, then we can get also the centroids for each of those. Once we have done that, then we can the data that after we have computed the 2 this constructs, that is that 2 components rather. So we can also convert the data points into those 2 components. That means for every data which has got x1, x2, x3, x4, x5, x6, we say that okay, x4 is not important, but x1, x2, x3 is correlated, and so is x5 and x6. So these 2 are correlated. So we say that, well, these 3 could be combined into principal component 1, and this 2 can be converted into principal component 2, right? And PC1 is equal to x1 plus x2 plus x3 with their weights. So there is a score and we can also add them up. So it's a linear combination, right? So instead of giving so many higher, so many features, we can reduce them into smaller features, into two abstract features, right? So PC1 and PC2, and those two are being plotted over here in PC1 on one axis and PC2 in another axis, and then we are also plotting their centroids, and then for each of these clusters we are also putting different colors using this, over here we have this scatter label, where is, let me look into it. So here we are measuring the centroids, and the centroids are given a color of black, marker is X, edge color white, line width is this, and then over here this is the CMAP 10. We are doing the scatter plot over here, and then we have somewhere a color scatter plot is created to show the clusters, and this part scatter level is cluster. So first what we will do is, if features are greater than 2, then only we will apply the PCA. Then PCA reduces the scale data to 2 components, as we discussed just now. And the same PCA is applied to centroids as well. So points and center appear in the same plot space. And if only 2 features exist, PCA is skipped and original scale data is plotted. So that, depending on the number of features, we can decide to do PCA or not. That is the code over here, if, else, and so on. Now finally we generate a color plot and to show the clusters and the separation, and we first, over here we can plot the scatter of the centroids first, and then we are also plotting the different, the results of our clustering, and you can use a color bar over here which actually plots this particular color to show that which value is plotted in which color and so on, and finally you can show the plot, and then we can save the data to d.urban_zones_clustered_k3.csv, and finally we can print the saved clusters as well. So that means this particular pathway. So that is what has been done, and you can see this is the final path, that is where that is the final plot that is being which shows the different clusters in different colors. So these are some of the references that we have used. And to conclude, clustering models such as K-means enable the discovery of natural groupings in multidimensional urban datasets by minimizing within cluster variance while revealing meaningful spatial and behavioral patterns without requiring labeled data. Thank you.